Thank you. It's my delight to be here in Goa and interact with so many smart people. We're going to go from a really philosophical and important discussion to a very technical discussion. So I hope you are ready for sort of a change in your thought process and mind today. So my talk today consists really of two parts. A useful part for practitioners and sort of a research part and sort of a deep dive that I hope that at least some of you will find interesting and compelling. So the first part is to introduce the event query language as a tool to conveniently search for malicious behavior in event streams or logs. And that was released just a few weeks ago in open source, so I'm introducing it here for the first time at nullcon. And second, I want to talk about a machine learning model to help discover unknown malicious behavior in logs. So you know something bad happened in here, tell me what was bad, okay? So for that second part, please understand that I'm a researcher and I can't help myself, and I'll be jumping into some detail about the machine learning model there. So for some context today, I've been studying artificial intelligence machine learning since the late 90s and now work with an excellent R&D team at Endgame, where I'm the chief scientist. And a small selection of things that you may have come across from Endgame and my team include Artemis, which is a way to interact with your enterprise network by, instead of a query language, by actually typing natural English. So show me process injection on my network, right? I type that. Or malware score, which is a lightweight standalone machine learning model, which actually we released an open source version called Ember, and anybody today can go download Ember and build their own next-gen AV model that useful for research. Most of my talks at research companies have actually been red team oriented, so I spent a lot of my career figuring out how to use machine learning against itself. So using machine learning to attack and evade a machine learning model. And what I'll be talking about today, of course, just prior to nullcon, we released EQL, the event query language, which is a useful way to both define analytics and to hunt, and also to do simple IOC search. So I just want to make sure, just for my information, can you raise your hand if you're familiar with the MITRE ATT&CK framework? Okay, awesome. I'm glad to see that a lot of people are getting to that. So hopefully many of you will become more and more familiar with this over time, but in fact, attack, ATT&CK, is sort of a knowledge base of attacker techniques and behaviors that span Windows and Mac and Linux, and can be used to navigate throughout that knowledge base. So the reason that attack is important, and I'll be talking about it today for context, is that it's become totally insufficient for you to defend against an adversary using simple indicator to compromise. Instead, if you focus on these sort of durable tactics and techniques that an adversary uses, you'll have much more success in finding an adversary who's living off the land or doing fileless attacks and things like that. So, for example, consider the attack at the bottom that suppose you have a trusted third party like a law firm who has access to your network. So he has a login. He gets access through a trusted account. He downloads and executes PowerShell scripts that are run in memory only. He maintains persistence through scheduling a task. He escalates his privileges using UAC, user access control bypass. He might move laterally using WinRM, which is a tool that probably most of you use. And he communicates with his command and control server using something like domain fronting over SSL, so you don't really know what's going on. So that is a logical chain of events that you're not going to find with an IOC. So you need to focus on behaviors, and attack helps you to find what those techniques and behaviors are. Okay, so I want to just, as an example that I'm going to refer to later, just dive in one cell of this MITRE ATT&CK framework, and it's squibbly-do. So this is using reg-serve32 to execute arbitrary code without launching it directly. So it's a way to register and execute a COM script using this registry, and actually the file never has to hit disk. It's actually, if your reg-serve is a domain and HTTP stack aware, so you can actually point it to the web, it will download and execute, and it looks like there's a legitimate Windows application that's running. So this is an important technique for attackers, because if I have sort of a whitelist policy for running, guess who's running my script? it's a legitimate Windows binary that's signed and trusted, and it never touched disk. So this is one example of those, and used by many threat groups, including APT22 and 19 and 32. And I'll be talking a little bit more. I'll use this as a use case in just a moment. So, okay, so 2 parts to my talk. Number 1, how do I find, if I know a pattern, what's an efficient way for me to find this? And I'm going to try to sell you on using an open source tool that we've just released called Event Query Language, and I'll show you how to use that with some examples. And I hope you'll find it's actually pretty easy and intuitive to use. And it's complementary in some sense to other tools like Sticks. There'll be a talk after this, or Sigma that some of you have used. So the second part of my talk, then let's suppose I don't know what exactly to search for. How can I try to learn, like, what are the things I should search for, right, from data? So that will be using machine learning. Okay, so event query language. Let me just introduce this in the following manner. Event query language is not, event query language is a way for you to take a pile of data, events of your choosing. Perhaps it's Windows event logs, maybe it's sysmon from sysinternals, or, for us, it's our Endgame event logs. And you, independent of the data schema, you can define in a way that equal is aware of process context and process trees. And by taking a single pass through the data, you can make very efficient queries. So because it's a single pass through the data, it's useful for 2 things. It's useful for logs, and it's also useful for event streams, so as they're happening on the system. And in fact, that's how Endgame uses this, is as events are flying by you, you build up this equal allows you to build this state model that kind of understands and interprets the state of things as you asked for them. And it will trigger when that analytic you've defined is satisfied. So the language is actually really simple. It looks a little bit like SQL, but it's for event languages. So that's why it's called event query language. So the second part of this, so you can go today to github.com, Endgame Inc. equal, and I can't today teach you how to use equal, but I can get you started. And go to this GitHub and check it out, and you're welcome to even follow along if you'd like. There's some examples in there. The second part is EqualLib, and EqualLib is a library of common techniques, so defenses for analytics for common attacker techniques. So if you're interested in looking in your own event logs for certain attacker behaviors, you can actually go today to EqualLib and use that as a basis. So essentially, if you're familiar with Red Canary's atomic red attack scripts that simulate attacker behavior, EqualLib kind of is mapping a one-to-one from atomic red to analytic against that. So today, the data I'm going to be using comes from Endgame, but you can, of course, use it for sysmon or Windows security events or what have you. Okay, so really quick, let me just dive in. And what does the data look like? The data comes is in its native form. It looks like JSON, and it has, there's really only a couple things that are important. It has an event type. So this is a process type, and it's a create process event. And it's being this create process event happens because of this command line, regserve32, which is pointing to the internet to download this script that will be launched, right? So notice that each event has an event type and a subtype, along with important data relating to the event. For example, the PID and the parent PID, the process path, the user and domain. And of course, you could have hundreds of events coming per second, per user, per endpoint. And so querying these events efficiently and intuitively is really important. So I'm going to actually stop the presentation and jump to some data so you can sort of appreciate what that might look like. And so here's a JSON file. It's full of all of the events that happened on my system when I launched Atomic Red. So it includes, for example, here's command.exe that is copying the Atomic Red files to the disk. So I'm capturing even the setup. So think of that as the dropper for my technique. And then it also includes my server 32 and all of the events that happen because of that. loading all these DLLs and executing the script, and finally, reaching out to the network, right? So what I could do to query this is in equal, I will say, let me query this file that contains all my events, process where command line equals, and I'm looking for the use of reg server 32 where it does anything that calls out to HTTP. And so when I do that, I'll then pipe it to JQ just to make the colors pretty for you all. And it finds the event that, in my maybe massive event log that corresponded to that. So if I were interested in, a simpler query, I could say, for example, let me find all the processes where anything happened, and let me just count the unique process names. So in this particular file, there are only 2 processes that were ever executed, reg server 32 and command.exe, each comprising 50% of all processes. So I hope that gives you just a hint of how sort of easy equal is to pour through a data set or an event stream. So I'm going to spend the next few slides going through some examples. And again, the use cases that my colleagues, when they released this, they wanted to cover not just IOC search, but also hunting. So looking for suspicious behavior on your system, and also straight up analytics. So can I use something to actually prevent malicious behavior? So first example, IOC search is not hunting, but it's an important part of your sort of daily hygiene. So to do that, you can say something as simple as this: process where process name equals evil.exe. So an equal query has these parts. There's this subject that specifies the event type you're interested in, and this predicate, this condition that specifies some Boolean logic that would satisfy the query. So I showed a demo already of that in action. Let's move from IOC search to something more interesting. So did any descendant of Microsoft Word create or modify an executable file? So I do that in the following way. I'm looking for any file where the file path was in Windows System 32 anything, and the file name was .exe, and it was a descendant of a process whose process name was WinWord. So that's a really intuitive way to say, show me something executed in that directory with that extension who's a descendant of WinWord. So you can make very sophisticated Boolean logic to find queries in this way. Okay, so here's another one. So here's another hunt. This is not analytic, but show me users mucking with the system like right now during the first few minutes of my talk. Give me any event. So this any event type is sort of a wildcard event where the username is not system, so any non-root user, and it happened during between these timestamps. And let me pipe it. So this pipe exists within equal. Count the username, right? So show me all the unique usernames. Another example that becomes interesting, many behaviors, and especially the ones I'm interested in the remainder of my talk, are not single events, but they're a chain of events that comprise an interesting behavior. So in some query languages, that requires some sophisticated inner joins, outer joins, and raise your hand, be honest, if you have to Google inner and outer join every time you do it in SQL, right? So instead, we want to make this really easy. In equal, all you do is say, join by username. So all these things can happen in any order, but they're going to share username in common. So in this case, the username executed the process who am I, hostname, tasklist, ipconfig, and net in any order. And let me show you all the unique usernames. So that would give people who are looking around on your system, right? All right. So last couple of examples for equal before we get into the remainder of the talk. But in many cases, order is important. So to define an ordered sequence, an ordered series of events, equal provides the sequence construct. So it's like the join construct, except every item in the sequence is described with an event query between the square brackets, but sequence, the order matters here. So sequences can optionally be constrained to a time span with this max span equals 1 hour. So you can imagine like a sliding window going through your event log or as it's coming from your event stream. or match common values with this by keyword. So in this case, we're looking for a file name, and I'm going to match its file path by the process path and the subsequent two events. So these things all share one attribute, its file path with these two process paths, and it has to happen in 1 hour. And so this would find a file that's created by a non-system user that first ran as a non-system process and later ran as a system-level process, all within an hour. Okay, one last example about equal and why order matters. So let me switch data sets from sort of an event log to, let's say I've detonated malware in a VM, and I'm looking at the API sequence calls. So if you're writing code for process injection, this is a sequence of things you must do for this type of remote shell injection. First, you open a process handle, you allocate, then you write process memory, create a remote thread, and you close. So these things happen in a sequence, and the thing that they share in common is hvictim, the handle that's first returned from open process, then passed as a parameter into the remaining. So I can search for this kind of behavior in an API sequence by doing exactly what seems logical. I say, find me a sequence that happens in this order. First, there's open process, where the thing I'm interested in is the return value. Then there's a virtual alloc x, where the thing I'm interested in is the arguments.h process, etc. And this would find sort of that remote shell injection. Okay, that is the tutorial of equal, and it's useful. Is there already a question? I'm happy to take it. Yeah, go ahead. Can you say it one more time? Can you say it one more time with the mic? I couldn't hear you very well.
So my question would be, like, if spawning a shell on a Windows machine using a MITRE shell, and we have injected that in a process, maybe consider svc host.exe, but that's a service which would be running from the time the system has started. So, like, going on all the SQL queries, now we are identifying if a new process has been spawned.
Oh, yeah, so it's a good question. In our event data, we have the notion of a unique PID. So we can find all the things and deobfuscate them so dedupe them because they have a unique PID, sort of a counter.
Okay.
Does that answer your question?
I mean, sort of, but yeah, my question was like SVC, like a process like SVC host.
Yeah.
It would be running from the start, and we have injected our payload into an already running process. So
I see. So before you started looking at events.
Yes.
Yeah. So maybe we can talk more offline about that. So this would depend on your data collection scheme. Endgame does this one way. I'm not here to sell you Endgame, although you should all buy it. I'm not here to sell you Endgame. We do that one way, but that would be up to you in your data collection process for your events. But if your event log has some notion of already running processes and you can detect injection events, then you can hunt for it in this way. Yeah, good question. Thank you. Okay, so all of what I've talked about so far is you kind of know what to search for, right? But there's a lot of things where you don't know a priori the specific sequence of events that would constitute malicious behavior. So for the next part of my talk, I want to talk about what's one way that you can kind of discover those events. And this is going to be a machine learning. So my background is machine learning first and security second. So my apologies. And I'll be talking about a way to use machine learning that I hope will motivate you to, in a way to discover these sort of semi-automatically. But first, I would like to step up on a soapbox for just one moment. You'll notice that in no point during my talk have I or will I claim that what I'm doing is artificial intelligence. Okay, so there's a reason for this. It's not technically wrong to call what most things in security are. It's not technically wrong to call it AI, but if I had my wish today is that we would all ban the phrase AI and ML forever in security. And let me tell you what I mean from a practitioner's perspective. So words, I might be fighting a losing battle here, but words are ultimately defined by their common usage. So I may lose. But let me tell you what, this is my first textbook in artificial intelligence that I got 20 years ago. And I want to give you my take and my context about AI and ML just for a moment before we set up what we'll call a machine learning model. So you can tell that this book is a modern approach, as its subtitle says, because of the cool 66 megahertz Pentium box with 8 megabytes of RAM shown on the cover here. But so seriously, there's a mismatch in our industry between perception and the practice of AI. And we all need to do a better job in our community about battling sort of the marketing buzzwords. And I think people mean no malintent. AI is sort of a common word that people latch onto. The problem is they're latching on mostly to the wrong notion. And so that's the thing we need to be a little bit more precise about. So probably what they're latching onto is more of, popular culture Jarvis, when in reality the machine learning deployed in your security product, while effective, is very narrowly focused, it's not adaptive, and it's not really intelligent at all. So when it comes down to it, you can get beneath some of this marketing hype and get some clarity about what AI means in InfoSec by remembering just a few simple things. And those are that in reality, the kind of AI that's making headlines today is called narrow AI. And narrow AI is very, very different from Jarvis. So narrow AI is, of course, what, let's say, good at playing the game of Go, or good at detecting your face, right? And too often, consumers confuse this concept of general AI in which a computer is able to reason and behave intelligently across many tasks with narrow AI. So furthermore, progress in narrow AI does not mean there's any progress in general AI. So Jan LeCun, the chief scientist at Facebook, has said that our advancement in general AI is about something far less than that of a rat, right? So even within narrow AI, 90% of what security products do today is actually machine learning. And I guess my plea to you is that we should be a little more precise and avoid sort of propagating some of those marketing terminologies when under the hood, machine learning is what really was happening. Let me be clear about that on the next page. So this is where this textbook comes in. So AI, machine learning, deep learning. To continue with my soapbox, let's be precise. So machine learning is an important subfield of AI that's very closely related to statistics and data mining. So statistics provides those formal inference with guarantees, and data mining is where a human is sort of digging through and discovering patterns in data using algorithms. And beginning at the bottom here, machine learning is about building predictive models from data. What I mean by that is, given an algorithm, you give an algorithm gobs and gobs of data, and it will summarize that data with a model, and then you throw the data away. And the model is an imperfect and flawed summary of the data. But it's useful because I can ask the model questions, I can ask it about facts that were never in the data. So I can use it to predict. So because it's imperfect, it will always have false positives. It will always have false negatives. It's imperfect. Even if your data was perfect, the model's not going to be perfect. So on the other hand, the broader definition of AI is about behaving and reasoning and interacting with the world. And sure, machine learning is a really important and major subfield of that, but it does not encompass everything. So for example, Tesla, self-driving car, is an AI because it behaves and reasons and interacts. But so is Clippy. Clippy is also an AI. I don't hear any security vendors bragging about having Clippy in their security product. So usually when one speaks of AI and security, it's most often they mean machine learning to predict and model. But they say AI for whatever reason. So again, if I had one wish for our industry today, that it's never again we would hear the words our product uses, quote unquote, this phrase, AI and machine learning, unless you happen to mean, I mean an autonomous agent and a predictive model, okay? So, in summary, while it's not incorrect, it's certainly imprecise, and I think for most of the population, especially outside of this room, it conjures up the wrong picture. All right, so that is the end of my soapbox, and I'll proceed with the talk. So how do we want to use machine learning to discover behavioral patterns in event streams and event logs? Here's something I'll propose to you. So the goal is here, I have a bunch of event logs, and I know that something bad happened in them. So let's take ransomware. I don't know how it happened, but all these event logs happened because my boxes got bricked. So what I'd like to do is I'd like to throw these at a machine learning model, and maybe with some human interaction, I like to spit out an equal query that will be, number one, interpretable, and number two, sort of generalize to all those events, all those malicious patterns in that event log. So it'll tell me what I should be searching for. The second goal of this is that I like to detect that not at the end. So it's useless if my ransomware has encrypted all my files, and then I say, oh, yep, ransomware. You got ransomware. We want to detect that as early as possible, maybe 1 or 2 file writes, for example. So goal number one, let's learn a general and robust analytic that's understandable because it's written in equal. I can understand it. It's easy to understand. And number two, I want to do that as early as possible. So in what follows, I'm going to go down this rabbit hole of building a machine learning model. And the thing that we're going to consider now is not just a process, but a parent process and all his children, and all the events that belong to that tree. And the reason is, of course, that many malware samples don't do the evil deeds themselves. They spawn children process to, for example, NetView or VSSadmin in the case of ransomware. So what follows when we monitor a process, we're actually monitoring all of the ordered events in the whole tree of that process. Okay, so let's jump into this machine learning model. And the first step we're going to do, there's going to be 3 steps. The first is we're going to prepare our data. We're going to change events in a textual representation into a numeric representation. Then we'll pass those on to a model, which will learn a better, more useful representation for it. And then we'll build some state on the sequence, and then we'll spit out an output, a maliciousness score. So the first step is the featurizing step. And it really consists of 2 parts. So suppose I have the following event, this file modification event. The first thing we are interested in is making this textual representation of an event into a series of numbers that the machine learning can deal with. And we're going to do that in a couple of steps. So the first is that I'm going to actually throw away most of the data. So there is no reason to believe that the model should learn PID or the username vagrant as an indicator of malicious behavior. In fact, if I leave username in here, probably what the machine learning model will key in on is that, hey, if you're running as a vagrant, it's bad, right? Because I'm detonating samples in a VM. So I'm going to throw out most of the data, PID and username. I don't really care where this process is running. I don't care when the process is running. I'm only use timestamp for ordering the events in the proper order. So what's left is file path. And furthermore, I don't care that it's in C Windows desktop vagrant test bytes. I'm going to normalize that to this shortened word desktop that sort of genericizes the runtime and the machine, right? So after that, then it's really easy to turn this. So this is actually a pair of items. There's an event type. So in this example, this is the third event type in a sequence. It's a file modify event, and there's some context. So I know the file path for that file type event. So I'm going to turn this into 2 sets of numbers. The first is I'm going to give a number to the event type. We'll call it 7, and then I'm going to change this text into a vector, and really easy, I'm going to just do a histogram of the characters in the path, in the normalized path. So there's something like 3 E's in there, so that's where this 3 comes from, right? So now I have numbers, and now I can actually turn this over. I'll do this for every event in my sequence, and I can turn this over to a machine learning model. So in its raw form, these numbers are not so useful to the machine learning. And here's where we're going to do a little bit deep dive. But all you really need to appreciate here is that machine learning can take this neural network that we're making can take these raw numbers and make more useful representations where usefulness is defined by the task the model is solving. So all it's going to do is I'll have two types of embeddings. It's going to map the 7 to a vector, and it's going to map this vector to a different vector. I'll concatenate them together, and all we really need to worry about is that there's this new representation that represents both the type and the context with the type. And that will be passed into a recurrent neural network. So a recurrent neural network is simply a function that takes as input two things, the current state and the current input, and it outputs two things, the updated state and the current output. That's it. So I'm just going to learn this function. In this case, we're using a gated recurrent unit, and I'm going to keep around the state internally. You know, when I update the state, I'll pass it back into itself, and I'll pass this output from this recurrent unit. So the reason we keep around state, of course, is that now when I pass in this vector for file modify, the state has already encapsulated the important parts of create, process, and registry write, so that the output from file modify is colored by the context of these previous events. I'll pass that through a simple neuron layer that will map the output of that vector output into a number between 0 and 1, where 0 is most likely benign and 1 is most likely malicious. So that's it. That's the end of this deep dive. I'm going to tell you, so I actually took 1 million benign processes from a corporate network, and I trained this model, and for a malicious set, I used 120 ransomware events. And this model is probably not something you'd want to stand up in production to detect events. That's not why we're interested in it today. But it does detect about 2/3 of the ransomware with a 1 in 100 false positive rate. So what we're interested in, though, is using this model that we've trained to tell the difference between ransomware and not ransomware, use it to discover patterns. So we can ask the model, what for this new sample that you've never seen before, what is the important part to you? And can I use that to build an equal rule? So here's a learned pattern by the model. Let me just describe this. So first, this is the ransomware DMA locker. And I'm showing on a timeline the events. So each vertical bar is represented by event, and the color of the bar is colored by how malicious or benign that sample is to the model. So blue means benign and red means more malicious, right? So we can see this model sort of builds evidence over time through many, many subsequent file writes that this is in fact bad. This is not good. This is a terrible model because it took me maybe 20 file writes before he's truly convinced that this is malicious. And in fact, it also has a number of annoying false negatives. So this ransomware, this Marlboro ransomware is not detected at all. And a false positive, and believe it or not, it's an AV product, right? That often is a false positive in many anti-malware engines. So this is a bad model. I'm going to show you how to make it better in the following slides using something really simple, but just as a baseline, in this example model, 95% of the ransomware that we detected, it took 65 events before we detected it. That boils down to about 21 registry operations and 10 file corruptions, writes or deletes. So can we do better? Can we make this earlier? And just for context, so this is an image showing on each column, I'm showing one of these colored plots. So everything starts out as benign, and as time progresses, things can get more and more malicious as determined by the model. So can we make this better? Can we move this yellow line up, which is the 95th percentile of detection? Can I move it up to, way up here? And maybe that's going to cost me some accuracy, but I don't care. I'm interested in the patterns. And more importantly, can we improve the patterns to make that detection happen earlier? And the answer is yes, it can do it in an insanely simple way. And I'll show you that. All you need to do actually is, instead of growing evidence over time, we're going to change our model so that it's able to look throughout time to find any malicious pattern during the entire history of the sequence. So by doing that, we'll have a new model that has a drop in efficacy. So now it can only detect over half of the ransomware at 1 in 100. Nevertheless, I hope you'll see that the patterns that it discovers are quite interesting. I'm going to show those patterns and show how we build equal rules based on them in the following slides. So in this model, again, look now at each column, and instead of this gradual increase from blue to red, now you see behavior that looks like blue, sudden jump to red, and in some cases, it jump back to blue. We don't care because at the first instance of red, that's when we call our process a ransomware. So the good thing about this model is that even though we've decreased our accuracy of detection of ransomware, we've increased the earliness. Now it only takes 2 file writes before we have discovered the malicious behavior. And the patterns I think you'll see are compelling. Okay, so this is the old model. It took a long time to detect this BitPaymer ransomware sample, and the new model detects it like this. So let me just walk through what the model tells us that BitPaymer is doing, and what you could do to write an equal rule to detect this BitPaymer sample. So if you notice, there's a creation event. If you can see it, a creation event, a process creation event, 2 of them, followed by a file modify event. So BitPaymer, if you're not aware, is ransomware that actually replicates itself into 2 alternate data streams. So it stores itself as an executable attached to a text file. So one of those, what I'm showing right here is apparently the second of those alternate data stream things. And what it's doing is the following. First, it's creating a process, command.exe, to launch via sysadmin to delete shadow copies. And then it's going to encrypt using the following scheme. It's going to encrypt a file and then rename that file, overwrite the file, then rename it to the file name.lock. As you can see, the machine learning is picking on exactly that. It sees this creation event where the arguments are via sysadmin.exe delete shadows, and it sees this file modify and rename. Immediately by the file modify, it already knows, yes, this is ransomware. So the rule that comes from this looks like this. Find me a sequence by this user that does the following. First, it runs via sysadmin to delete shadow copies, and then it renames the file name to .lock. That's it. So this was not discovered automatically, but in a semi-automated way. It told me where to look, where the boundary of interesting events were, and then what I did is I just jumped to those logs and looked for the important features. And it told me that via sysadmin was important and .lock was important. And so it's easy for me to write that rule. So a few more examples. This is DMA Locker, ransomware. DMA Locker does the following. He first drops a ransom note, then he disables the Windows firewall and update, and then he starts encrypting files via overwrite. The old model took quite a long time, if you recall, to sort of convict this ransomware sample. And the new model, it's quite abrupt. So it takes a few registry writes, but after the first file create, second file overwrite, he's already quite convinced that this is ransomware. And the equal model that we've learned because of this looks like the following. Find me a file, create event, where the file name was cryptinfo.txt, that's the ransom note. Find me a registry modification that happens to the Windows firewall registry key, and then find me any file overwrite event. And that's sufficient to find this sample with no false positives in my entire data set. Another, one last example, this is from the Marlboro sample. The old model actually misses completely, and the new model finds it with this abrupt change here. And what's happening, it tells us that what's important is, again, deleting shadow copies with via sysadmin, creating this database file that sort of apparently sort of keeps a log of what files have been encrypted. It makes a DNS request, and I've removed that domain. And then it encrypts the media archives source files to filename.extension.oops. So as you can see, and then deletes the original file. So you can see that here. You see the DNS requests, you see the file delete event, file create event. So as soon as we see this first file delete event, the model is already certain that it's ransomware. And the equal query that you could do with this is as follows. I do a via sysadmin, delete shadow copy, I look for a create event, and I look for .oops. Okay, so models aren't perfect. As a machine learning researcher, I'll be the first to tell you this. So I want to show you explicitly a false negative and a false positive. So in this case, the false negative from the previous model for this OCamE sample, teardrop, which I actually don't believe the Microsoft label here, but for our model looks like this. So it found something that it's maybe slightly suspicious, but it didn't sort of elevate it to the above a threshold where we'd call it ransomware. This sample, as it turns out, is actually not the main teardrop sample, but is actually like an evasion tool that disables Windows Defender services and modifies console tracing to hide its footprints. So it's maybe paving the way for the OCamE sample to be dropped. And so maybe that's why this is a false negative in this case. A false positive. So both the old model and the new model discovered this sample, which is false positive. It turns out to be AVG update service. And here's where your false positives. If you look, there's a bunch of registry modifications filed by some overwrite and a file create event. And if you remember from the previous samples, that's a very common rule, a very common sequence in that ransomware. So the good news here is for each of these false positives, I can create a very explainable way using equal to determine exactly why they're false positives. And furthermore, I could actually whitelist this. These all happen to be signed valid, signed binaries with valid signatures, so you could whitelist those. Okay, I am nearing the completion of my talk. I just have a summary slide. I want to just take a step back. We've taken a deep dive down machine learning approach to discover from just sequences where in here is something that's malicious, and use that to derive an equal rule that can, in a really explainable way. So equal is nice because I can deploy it easily. I can do it today. I don't have to like invent some new machine learning trickery to use it on my system. And I know exactly what it's doing. I know exactly what it's looking for. And that's one of the sort of difficult problems that vendors face with machine learning is they can't often tell you why a detection happened. But with a query language, you can. This model only turned out to be 150 kilobytes, and it's probably too crude for standalone detection, but we can create these rules in that way. So my final slide today, if you take nothing else from this talk today, it's number one, I hope that you'll become familiar with the MITRE ATT&CK framework for enterprise. You can do so by just going to this website. It has wonderful documentation. You can read about use cases of each of these tactics and become familiar with how adversaries and very high-profile campaigns have done evil things without leaving a lot of IOCs around. And that should hopefully motivate for you why you should be hunting for behaviors rather than indicators of compromise or just malware alone, anti-malware detection. Secondly, I hope that you've seen that equal is actually pretty easy to use and read. You can download this today. Go to GitHub equal. And furthermore, there's an analytics library that's baked in and ready to go. You can start hunting with this in your own environment today with equallib. And if you follow Event Queryling on Twitter, so I am not an author of the query language, but my very smart colleagues at Endgame who did invent this, they from time to time post news and novel detection techniques that come out of band from the product releases. So it's an interesting account to follow. And lastly, if you do nothing else today, for goodness sake, let's please agree to stop saying AI and ML and be a little more precise, unless you happen to mean autonomous agents and predictive models. Thank you. Appreciate your time. I think we have time for questions. I'm happy to take any. I don't think we have a connector yet. I can show you offline. It's very easy to, so all you need to do is, it's very easy to wire up. So. Yeah. It would be really easy to wire up. Right now it's baked into other things, but yeah.
Do we have any other questions?
Hi, this side. As you have mentioned that feature extraction is one of the important factors while doing our machine learning algorithm, right? So My question is, so as you have mentioned the feature extraction, only the file name you have considered, right?
In that example, actually, we consider many fields.
Yes.
Yeah.
So I understood that, but what about using something like CNN and using feature extraction with that, and how to generalize those kind of feature extraction, and how EQL can actually help us that which feature extraction is useful for generalizing the classification?
So you could use CNN too, but guess what? You can't. You'd still have to do the pre-processing we talked about. You have to run a CNN on numbers, not characters. So you'd have to, at the very least, transfer your file name into a sequence of numbers. So those are all possibles. I didn't try very hard to optimize this model, but that would be an interesting line of research for you to look at.
Okay, thanks. Very nice talk. Thank you.
Any other questions?
Yeah, go ahead. There's a...
So have you tested it against adversarial learning attacks? Adversarial learning attacks.
Adversarial learning attacks against this model are certainly possible. Actually, I just reviewed an ICML paper about attacking sequential models in this way. Yeah, I've not looked into that. I've done that for a lot of my career, and I learned that it's, as has been said earlier, it's a lot harder to be blue team than red team. Red team's really easy. It's really easy to attack. So I would not doubt that you could find ways of creating ransomware that did enough things. It learned what benign event to inject in order to bypass completely this model. No problem. No problem.
Thank you.
Yep.
Any other questions?
So IP address and DNS names can change. So how do you handle that? Like, what's your suggestion?
Yeah. So in this example, I think we actually scrubbed out IP altogether. DNS I might have kept, but that's a tunable parameter that you could do. For more generally for equal, that's going to be in your log, and that's a useful IOC that you can hunt for. But you can use wildcard searches, for example, or you can just write analytics that do not depend on sort of the more brittle elements such as IP address and DNS.
Can I insert reputation data in this and then get clarity? So is that possible?
You can put anything in here you want so long. So here we're talking about the data behind equal. Anything you want so far as it has an event type, a timestamp. That might be it. But other than that, the language is just reading the keys of a JSON object. So as long as you have these basic keys around, you might have to tie a process ID to it too. But once you have those basic things, you can put whatever decorations around your data that you'd like to.
Thank you very much.
Yep.
When you have the JSON which has the list of events, without having to categorize for the event type, if we have to convert to binary, what formats would you suggest? If
you have to convert JSON to binary?
To a vector, to be passed to the model.
Oh, for the machine learning.
Huh.
Okay, so one more time. So for the machine learning model, if I have a JSON blob and I want to convert that for the machine learning model, what do you do? Is that the question?
Yeah.
Yeah. So again, you would have to, I'm happy to talk in more detail, but you'd have to come up with a way to transfer all of that, each structure in the JSON block with many fields, take them in an order, a predefined order, maybe alphabetical order, and for each key, spit out a unique vector and concatenate them all together. So I have one vector of numbers. And that is mostly art, not science.
So my question is are there any factors that can affect the way the model behaves? Is choosing my vector or the structure of my vector with respect to ordering or structuring the events and their relative importance, does it really affect, or if it affects, to what extent does it affect the model?
Yeah, it does.
This particular model you chose.
It certainly affects it. The things that this model cared most about, actually, remember there was two parts that I told the model to care about. It was the event type and the context. So that would be like file create events and what's the file name and extension, right? The thing it cared most about was just the event type.
Right.
And the context was of less importance. And that could be an indicator that I didn't do a very careful enough job to define what you're saying. Taking
No, I understand that was why the man plus machine part was put into this process. I was just thinking, could it be generalized not for just ransomware, but a wide variety of malicious events to be detected for patterns?
Absolutely, yeah. Ransomware is just an interesting case. I used ransomware because everybody knows ransomware when they see it. Like when you see the events, you know it's happening. Other malicious activity is harder. So ransomware was just an interesting case study for this talk. But in reality, what you and I are interested in, what we're doing in Endgame is, it's not just ransomware, there's lots of attack patterns. So take every malicious script on Atomic Red, can I build a model to detect those? The answer is yes.
Thank you.
Yeah.
Any other questions? Thank you, sir.